Hello, my name is Moise Mowema from the Department of Mechanical and Aerospace Engineering at Carleton University, Ottawa, Ontario, Canada. And today I'll be presenting a QUEST-based Kalman filter and LQR for satellite attitude control. Looking at the outline we have for today, we'll start off with the abbreviation and preliminaries used throughout the presentation, then look at the attitude estimation problem, followed by the problem formulation. Then we'll look at the Kalman filter and controller design, explore the simulation results, and finally conclude the presentation. Starting off with the abbreviation and preliminaries, Q denotes unit quaternion vector, Q dot denotes quaternion derivative, omega denotes angular velocity, SO3 denotes special orthogonal group of order 3, IN denotes identity matrix with dimension n by n. The following is a skew-symmetric operation. LTI stands for linear time invariant, QUEST stands for quaternion estimator, and LQR stands for linear quadratic regulator. Starting off with the attitude estimation problem, the applications. Attitude determination and control is essential for almost spacecraft mission operation success. For example, it's used to orient solar arrays such that the spacecraft obtains the maximum power possible. It's also used to orient payloads towards point of interest so that more accurate data can be obtained. And finally, it can be used to point antennas towards ground stations so that maximum data can be downlinked. Attitude estimation and control problems are not just limited to spacecraft missions, but are also considered major subtasks in robotic applications such as UAVs, surgical robots, and autonomous vehicles. Attitude of a system is represented by rotation transformation that relates two reference frames, a reference frame fixed to that system, and an external reference frame. The parametrization used to represent attitude can be singular or present discontinuities. The following table shows the most common representations for attitude. As can be seen from the table, rotation matrix and unit quaternion are the only possible choices. However, unit quaternion is the preferred choice for attitude estimation because it is the lowest dimensional parametrization that is free from singularities. As such, to avoid problems associated with global three-dimensional parametrization, attitude quaternion has been used throughout the research. Looking at the attitude estimation, attitude is based off sensor measurements that are always corrupted with noise, drift, and bias. The problem with that is the true attitude is not equal to the measured or reconstructed attitude. One possible solution would be a filter to smooth out the noise present in the measurements. An even better solution would be to use a deterministic three-axis attitude determination algorithm like QUEST, and then filter the reconstructed attitude using a Kalman filter. And the way this would work is illustrated in the block diagram below. So low-cost IMU sensors would feed their data into an attitude reconstruction algorithm like QUEST. And then the uncertain reconstructed attitude would be filtered using a Kalman filter, and a better estimated attitude quaternion would be obtained. So from the estimated full dynamical state vector, and if you have the desired attitude, the error between the two can be calculated. A signal can then be fed to the controller such that the actuators force the current attitude to match the desired attitude. And this encompasses the scope of the paper. The whole process is illustrated in the figure below. Looking at the problem formulation, the attitude dynamics of a rigid satellite can be expressed using the equation below, where J is the tensor velocity, omega is the triaxial angular velocity from the gyroscope, and tau is in-body axis vector of torques applied to the satellite, which also includes external perturbations. The quaternion satellite dynamics satisfy the following kinematic equations, whereby the omega with the skew-symmetric operation can be expanded in equation 4, and the state space dynamic equation is shown. In order to program this, the satellite dynamics need to be discretized, and the discretized state space kinematics and dynamics of the attitude of satellites are shown in the following equations. The desired dynamics are also given by the following equations. Looking at the filter design, Kalman filter can be initiated from the following linear state space model. Kalman filter proceeds by iteration of 3 steps: measurements update, vector state reset, and propagation to the next measurement time. The measurement update step updates the error state vector. The reset moves the updated information from the error state to the global attitude representation and resets the components of the error state to 0. The propagation step propagates the global variables to the time of the next representation. This is illustrated in the figure below. Looking at the controller design, LQR is based off a linear time invariant system that follows the following state space representation. And the cost function of the performance is constructed in form of quadratic terms which track performance and control efforts. The objective in LQR entails cost minimizing, and the corresponding control input solution can be obtained using the well-known Riccati equation. The controller is of the following form, and the feedback gain K can be found by minimizing the cost function shown, where X represents the error, Q is a semi-positive definite matrix, R is a positive definite matrix, and X subscript ref is the corresponding reference matrix. So using the Hamilton-Jacobi-Bellman equation, the optimal control policy is as follows. And for an LTI system independent of X naught, the control policy is as follows, where P is the unique solution to the algebraic Riccati solution equation. The satellite initialization parameters used in the simulation are, so we suppose the spacecraft is spinning at an initial constant angular velocity shown. The sampling rate of the gyroscope is assumed to be 1000 Hz, and the attitude determination process is operated for 30 seconds. The gyro drift bias is set to the following values, while the gyro noises estimate is set to the following values. Magnetometer noise and bias are both set to the values shown. The accelerometer bias and noise are set to the values shown, respectively. Center confidence is set to the following values. The Kalman filter initialization parameters, the measurement covariance matrix is a 4x4 identity matrix of 0.1, while the process noise is a 4x4 identity matrix of 0.02. The true accelerometer and magnetometer measurements are set to the following values, respectively. The simulation results that were performed in MATLAB are illustrated below. As can be seen from the graphs, the estimated attitude uses measurements to update the predicted attitude and with minor steady state errors, thus illustrating the efficiency of the two-step filtering architecture in cases where sensor measurements are corrupted with noise. So the error between the estimated and measured attitude, as mentioned, is minimal and approaches 0, as shown in the graphs below. The LQR initialization parameters, the satellite inertia matrix is assumed to be a diagonal matrix of the following values, and the following weighting matrices were empirically found to be a 3x3 identity matrix of 0.01 and a 6x6 identity matrix of 10 to the power of -7. The input torque and angular velocity are initially set to 0, and the reference quaternion is set to the following values. The simulations are performed where the error that we're trying to minimize is obtained by subtracting the estimated filtered attitude from the true attitude. The quaternion-based attitude simulation results are shown below. As can be seen, the steady-state error remains minor with the same Kalman filter initialization values, thereby illustrating the effectiveness of the controller in making quaternion attitude and angular velocity approach the reference values that were shown previously. In summary, accurate attitude estimation is essential for spacecraft guidance, navigation, and control, and is also a major subtask in other applications as well. Attitude estimate becomes challenging when low-cost IMU sensors are used because the measurements become corrupted with noise, drift, and bias. A two-step filter architecture is proposed for better attitude estimation, whereby the attitude is first reconstructed using QUEST, and the reconstructed attitude is then filtered to obtain a better estimate attitude. The LQR algorithm is then used to minimize the error between the estimated and the desired reference attitude. And numerical results are presented to illustrate the effectiveness of the proposed attitude estimation and control strategy. Thank you.